Hi, everyone. Thanks for coming. It's fantastic to see so many, seriously great Bitcoiners in one place, one time. Um, these things, I think, Justin was talking about the importance of meetups earlier, importance of conferences, things like this, where you can really kind of spread knowledge and then let it disseminate out into the world as people go home. So we really appreciate you coming out, supporting the cause. Uh, I'm going to keep this pretty quick because we're about to do I guess like a workshop that teaches you about mining, proof of work specifically, which is what kind of powers Bitcoin, what keeps it secure, what makes it better than a lot of the shit coins out there. So I know there's a lot of you out here who have been talking about Cardano and insert shitcoin here. I hope you're in the room and can learn a little bit about really why Bitcoin is secure, how it fundamentally works. And so a little bit of background on me. I'll do a soft shill. We had some people up here. Will Reeves from Fold, Ken Kruger from Pay with Moon. I'm starting another company called the Bitcoin Company. We got some people in the crowd. Dread, D++, who will be up here in a second. Ben the Carman, fantastic developer. So we're all working on this project together. Our goal is to bring Bitcoin to the world, just like many of these companies. Azteco, strange video, but if you don't know what they do, you just scan this code and they send you Bitcoin. So I'll do their pitch for them. But yeah, what we're working on is something pretty similar to what Fold and Pay with Moon have now. We have a kind of loyalty program that lets you convert or pay Bitcoin and buy gift cards or open loop Visa cards. That's coming out very soon. We're going to be beta testing here in the next week or two. So I guess if you guys want in on the beta, go to thebitcoincompany.com and sign up. That's really all I'm going to do to shill this so far. We have a lot more big plans to build an exchange, to build banking services. But for now, we're giving out rewards and trying to stimulate this circular economy. But without further ado, because I know Dee is kind of crunched on time, we're going to start the Proof of Workshop, which is a clever name that she came up with. It's going to teach you about Bitcoin mining. You're going to do some mining on your phone, understand how proof of work works, and we're going to give away a bunch of free Bitcoin in the process.
I'm going to use this mic. All right. I'm D++. I'm so happy to be here. Thank you all for coming. I am going to be explaining how Bitcoin mining works. I call it demystifying mining proof of workshop. So before we start the workshop, let's kind of get acquainted with each other. How many of you in the audience are miners? That can be home mining, that can be mining at scale. Awesome. Okay, and how many of you in the audience would consider yourselves to be technologists? You're developers, you're tech savvy. Okay, how many of you aren't really particularly tech savvy? So I'm feeling like half and half. Okay, well, regardless of your technical skill level, I'm confident that we can all understand how mining works today. Now, when I set off to attempt to understand Bitcoin mining, I was very confused. I was reading articles in mainstream media that were saying things like, miners are competing to crack crazy cryptographic puzzles, or they're competing to solve really difficult math problems. And it makes no sense. It made zero sense to me then. So you can imagine I was delighted when I found that it's way, way simpler than that. It's extraordinarily simple what's happening. There are no crazy cryptographic puzzles. There are no difficult math problems. In fact, a show of hands, how many of you here today can compare two numbers? You can look at two numbers and ascertain which one is larger and which one is smaller, or maybe perhaps they're equal. Okay, anyone in the audience cannot compare two numbers? All right, unfortunately, that's Fish over there. I am gonna have to ask you to leave. I really want 100% success rate today. And if you can't compare two numbers, I am going to have to ask you to leave. Now, I learned how to compare two numbers in second grade. And if you can do that, you can understand mining. So we're going to talk about what numbers are going to be compared. But before we get to that, I need to introduce one concept to you, and that is hashing. Now, how many of you are familiar with hashing? Okay, 50-50 again. Okay, so what is hashing? So a hash is a function that takes something in and spits something out. Okay, we give it a thing, it gives us a thing back. So let's talk about what goes in and what comes out. Now, what goes into a hash function is anything. It's the kitchen sink. I can input a number, a letter, a word, a sentence, a paragraph, an entire book, the entire contents of my entire hard drive, a cat video, a cat photo, or a single character. Okay, so the input is any arbitrary input of any arbitrary length. Got it? Now the output, regardless of the length of the input, will be of fixed length. And because the output is always of fixed length, you can think of that output as being like a summary of the input, or a fingerprint, a unique fingerprint. The output looks random. It's actually not. It's deterministic, meaning the same input always will yield the same output. And let's talk about what's happening under the hood. Now, inside of this function, what are we doing? We're slicing, we're dicing, we're blenderizing that input to the point of no return. Meaning, when I take bananas, strawberries, kale, spinach, orange juice, that's my favorite smoothie, and I blenderize it, I can't unblenderize it, right? It's a one-way function. So similarly, hashing is a one-way function. We can go in, but we cannot come out. Meaning, if I were to hash my password and show you that fingerprint, that summary, you would have zero information about what my password is because you cannot undo the hashing operation. The only way you could know my password would be if you were to guess and check and compare your hash with mine. If they're equal, you cracked my password, but you'd have to brute force it. Now, if my favorite websites are smart, hopefully they're saving a hash of my password on their server and not my password in the clear. So if someone were to compromise that data, they wouldn't see my password. So hashing is used everywhere, all over the internet. It's used extensively in cryptography. It is not unique to Bitcoin. It's used in Bitcoin in a number of places, in transactions, in key generation, in addresses, and it's used extensively also in mining. So let's review. A hash is a function that takes an input of what length? Any length, and it will always output a fixed length output. It's a summary, it's a fingerprint, it's deterministic, same input gives us the same output. It's a one-way function like a trapdoor. When I fall down a trapdoor, it's easy to fall in, but I can't get back out. I can't reverse the hash function. That's important. Now, any minor change to the input will yield an entirely different hash. Entirely different. And there's no telling how that hash will look until we hash around and find out. How's everybody feeling about the concept of hashing? You feeling good about it? Okay. So you understand hashing. You can compare two numbers. So we can all mine Bitcoin. This is going to be really fun. Now, like I said, hashing predates Bitcoin. There's different types of hash functions, different algorithms, if you will. Can anybody tell me what hash algorithm Satoshi Nakamoto selected for Bitcoin? There's a few, but the one we use the most and the one we use, okay, SHA-256. Now, the SHA part is a very creative acronym. It stands for Secure Hash Algorithm. What does the 256 denote? Someone said bits. What does that mean? The length of the output. So when I told you that the output was going to be a fixed length, I wasn't lying. In the case of SHA-256, the output is 256 bits, 256 ones and zeros, 256 binary digits. A little hard for us humans to read, but computers read these binary digits just fine. Okay, so let's try this for ourselves. Let's actually try hashing. If anyone has access to a Linux-style command line interface, you can do a SHA-256 sum. And if you don't have a Linux terminal available, don't worry. I was kind enough to create something for you. So we're going to head over to a URL. You're welcome to follow along. Oh, internet would help. What do you guys think the Wi-Fi password is? I don't know. Detroit? Oh. Well, I was on the guest Wi-Fi, and it looks like it disconnected me. So it's Detroit. 301? Okay. All right, let's see if this Wi-Fi works. Otherwise, we're going to get a Wi-Fi hotspot. And while I'm waiting to connect to the internet, what you guys can do is you can try this hashing program that I created for you. It's d++.me. Go ahead and pull out your phones if you feel inclined to. And let's try hashing something together. So I'm going to hash a word or a short phrase. Can anybody give me a word or a short phrase? Unconfiscatable. Yeah, so if you want to play along, you can go to d++, spelled out, .me, /SHA-256. So I don't know if I spelled this right, but unconfiscatable, when hashed, yields this result. Now, this result is a number. And I wasn't lying to you when I said it was going to be a 256-bit number. I simply compressed that number. I compressed it into 64 digits. It's a little easier for us humans to read this style of number format. There are some letters. It's a very highly compressed number format, so don't worry about the letters. Understand that it's a number. Does everybody understand that the output of a hash is simply a very large number? It's almost infinitely large. It's very hard for our human minds to comprehend the magnitude of a 32-byte number. This is the same size as your private keys to your Bitcoin. Okay, so it's a very large number. Now, if I were to make any change to this input, the output would change entirely and would reveal no information about what was changed, right? And the only way to see how the result changes is to actually hash. I can't predict what's going to happen. So if I put exclamation point at the end, the result is completely different. Can everybody see that? One more. Completely different result. No relation to the previous result whatsoever. It looks random, but it's not, because it's deterministic. Now, how many of you have looked inside of the guts of SHA? What developers are kind of in the audience that have looked inside? Okay, so if you're a developer, we're going to treat this like a black box, meaning I'm not going to tell you what's happening inside of this blender. But if you are a developer, what's happening under the hood is some bitwise rotation, some bit shifting, some addition, some constants, and some XORing. Outside of the scope of today's lesson. Don't worry about it. We'll do another one, like next time we'll do SHA by hand. Who would enjoy that? It'll be fun. Next time we'll do it. But today we're not going to go into the inner workings of SHA. We're just going to treat it like a black box, and we all understand it's a deterministic one-way function, takes an input of any arbitrary length, returns a fingerprint of fixed length, okay? Any change to the input yields a entirely different fixed output. Right, now the output is called a hash. Sometimes it's called a digest. Can anybody tell me in cryptography what we like to call the input to a hash function? It has kind of a cool name. What do we call it? You can call it a message, but it's often called, what's the input to a hash function? Come on, think of lightning. What are we revealing in those HTLCs? A preimage. Who said preimage? Perfect, okay. So the input to a hash function is called a preimage. I just think that's a cool word. I think it sounds like a cool new wave band or something. I don't know, preimage. So, okay, so we're feeling good about SHA. Great. Okay, so let's get back to the comparison of two numbers, right? What numbers are we comparing? Well, the first number we're going to compare is going to be a hash. It's just a really big number. Now, I mentioned you can hash anything. Could I hash an entire Bitcoin block? I could throw a block into SHA. I could, yes. Now, the result of that hash is a number, and I'm going to compare it to a given target, okay? The target is another number. They're two numbers. Now, if the hash of my block is less than a given target, and we can all do less than, right? I mined a Bitcoin block. I found a block that follows the rules of Bitcoin. I get rewarded with the honor of adding my block to the immutable Bitcoin blockchain, which is an open, permissionless database. I get to add my block to the blockchain, and I get rewarded with 6.25 baby just born Bitcoin, plus all of the fees from all of the transactions included in my block. All I have to do is find a hash that's less than a target, and I found a block. It's that simple. So, show of hands, how many of you are finding today that mining is actually a more simple process than you would have previously thought? There's no cryptographic crazy puzzles, math problems. It's a comparison of two numbers. You get a number that's less than a target. You get 6.25 Bitcoin, okay? We're gonna see an example, yes we are. So I took the time to write a program for you in JavaScript that will show you an example of what's happening. So this is a Bitcoin block. The block has a block header with some metadata and some transactions in the body of the block. Now I'm gonna take this whole block, I'm gonna throw it into SHA. It's gonna give me 256 bits, a fixed length number. So let's try it. I'm gonna hash this block, okay? And I'm gonna compare the result of that hash to a given target, which is a number. And the target is here. Now it's a weird number again because there's some letters, but all I'm looking for is to see if my hash is less than a given target. So when I hash my block, I get this result. EC3B, again, it's a weird compressed number, but it's a huge number. So I want to compare this to a given target. Now, because these numbers have the same amount of digits, an easy way of comparing, and we can all compare, an easy way of comparing would be to simply look at those leading zeros in the beginning of the number, right? So if our hash has the same number or more of leading zeros, that means it's less than or equal to the target, right? Does that make sense? Yeah, okay, so these numbers, they're really big. They have the same amount of digits, in this case 64. I can look at the two numbers and I can ascertain which one is smaller by looking at the number of zeros, leading zeros, in the beginning of that number because they have the same amount of digits. Now in this case, my target has only one zero. My hash, however, has how many zeros? So is my hash less than our target? No, okay, it's not less than, but if it's less than the target, I get 6.25 Bitcoin, and I really want 6.25 Bitcoin. So I showed you when I made a very minor change to our input that the hash changed completely. And there was no way of knowing how it would change until we hashed around and found out. So could I add something random to the Bitcoin block to change the hash? Could I add, say, a random number somewhere in the block, just plug it in, hash the new block, and see if that new hash is less than the target? Could I do that? Okay, this might sound a little silly or even archaic, but believe it or not, this is entirely how Bitcoin works. Mining is a process of guessing and checking random numbers, plugging them into blocks, checking if the resulting hash is less than a target, and repeating the process until we find that number that, when plugged in, gives us a hash that's beneath that threshold. Now, there's a special name for that number that we're looking for. What do we call that random number that we plug in to the block? It's called a nonce. A nonce stands for a number used once. They're used extensively in cryptography. If I find the nonce that solves the block, I call it the golden nonce. Okay, so let's try putting a random number in here and seeing what happens to the hash result. Can someone just tell me of their favorite number? Oh my gosh, okay. 23? 69, 23, okay. We'll try 23. Now take a look at the block header hash before and after I add the nonce value. Like I said, the block header hash changed completely, but is the new hash less than our target? Does it have those leading zeros that we want? It does not. So can someone give me another number? 2. No luck. 73. Well, I cheated a little bit because I tried some of these at home. I tried some of these at home, and I kind of remembered that 125 worked. Now, there's more than one winner, meaning there's more than one number that I can plug in here that will give us a valid block. I happen to remember that 125 worked, and wow, we found the golden nonce. Lucky number 125, when plugged into this block, yields a hash that is less than our given target. Can you see this 0 here? So we found a block. This is exactly how Bitcoin works. The only difference between my program that I wrote for you guys with love and Bitcoin mainnet, there's only one difference. It's the same algorithm. It's the same process. The only difference is what? Is that on the Bitcoin mainnet, their difficulty target is a much smaller number. Okay? It is much, much, much smaller than the target that we're using today, because it's a lot harder to find a block, right? Okay, so I have an idea. How would you guys feel about mining Bitcoin today? Should we mine? So here's what I'm thinking. I'm thinking of adjusting the difficulty. I'm thinking of making it a little harder. So if I wanted to make it harder to find a block, I'm going to change that difficulty target, which is a number, right? So if I want it to be harder to find a block, would I make the difficulty target smaller or bigger? Who votes smaller? Okay, who votes bigger? The consensus, I think, is smaller, and you would be correct. So if that number is smaller, it's going to be less likely that a hash will then be beneath that threshold. Does that make sense? It makes it harder to find Bitcoin. And this is what Bitcoin does, by the way, every 2016 blocks. It looks at the previous 2016 blocks. Actually, I think there's a bug where it ignores one of them, but that aside. And it adjusts that difficulty target. Okay, so here's what I'm thinking. I think we're gonna mine a block, and we're gonna win Bitcoin, meaning if you find a golden nonce, you're gonna get a block reward. Now, I'm not gonna give you 6.25 Bitcoin, sorry, but I'm thinking I'm feeling generous. I'm thinking whoever finds the block is going to get 250,000 Satoshis. Sound good? Okay, so here's what's going to happen. I'm going to give you a URL. You pull out your phones, get your browser ready. I'm going to give you a URL. The second you get that URL, you're going to plug it into your favorite browser. You're going to brute force guess and check that nonce value just like we do in Bitcoin. And if you find that golden nonce, you're not going to raise your hand. You're not going to be polite. You're just going to yell it out. And the first person to yell it out is going to get 250,000 Satoshis. Sound good? Does everybody have their phones ready? Okay, now I did make my simulator quite accurate, meaning there is a upper limit to that nonce value. It's about 4 billion. So if you're wondering why you can't put in a number that's more than 4 billion, it's simply because that's how Bitcoin works. It's only a 32-bit number, which is actually quite small. Any questions before we get started? We can compare two numbers, we can guess and check random nonce values. This brute force process, again, is exactly how mining works. Who's ready for the URL? Okay, I'm gonna give you the URL. I think I'm gonna pump it up and play some music. You're not gonna be polite. You're just going to blurt out the answer. Sound good? Okay, I think we're ready. First, let's pump it up. Let's pump it up. I got some music for you guys. And hopefully Xfrog has some audio for me. Well, the audio may or may not work, but we've got a cool video for you. All right, and let's give you that URL. I'm thinking we're gonna do, all right, d++.me/mine. Starting now. It's d++.me/mine. d++.me/mine. Gotta scream it out. All right, let's not trust her. I'm not gonna trust her. That's something we gotta verify. Remember, don't trust, verify? What'd she say it was? 14475. Okay, 1475. All right, congrats to the lucky winner. So you're getting 250,000 Satoshis. I don't know. Come find me after. We'll do a Bitcoin or a Lightning transaction. Your choice. All right, any questions? She guessed. How'd you do it? You guessed and checked random values. That's exactly how Bitcoin works. Question over here. It did not. So what we do in Bitcoin is we look at the length of the blocks coming in. We want them to be around 10 minutes. If they come in too fast, we make that target bigger or smaller. smaller. If they come in too slow, we make the target bigger or smaller. Okay, so who wants another try? Should we do another try? Do you guys want to squeeze another 250K sats out of me? Okay. Is there a method to the madness? What do you guys think? Is there a method to this brute force madness? No. There's no strategy. There's no cheating. You cannot cheat this. She guessed him. What's up, Neil? What do you guys think? You want to make it harder? What do you think, Dred? Go ahead. There can. Well, let's look at this difficulty target. So this is a compressed number. It's got 2 zeros, but really in binary, that's 8, 9, 10. So really it's 10 zeros in binary. 2 to the 10 is 1,024. 1 in 1,024 on average guesses will solve this block. So yes, there are a lot of possible nonces that will win. And she happened to find one. Okay, so you guys want to make it harder on yourselves? So you want to adjust the difficulty target down, meaning it's harder to find a block? Okay, we can do that if you insist. Why don't we do one more at this target? Okay, so same URL, go. You found it already? Nope. Oh? Am I playing that? Okay. 24175. One more time. Okay. All right. You guys were like cheating. You were noncing while I was talking. Probably because he's on a different URL. You gotta use the URL that I gave you. So who gave me 1987? Okay, come find me after. You're getting 250K sats. Now I think it's still too easy. So here's what I'm gonna do. I'm gonna increase the difficulty, meaning I'm going to decrease the difficulty target. Okay, so I'm gonna give you a new URL. Don't use the old URL, okay? This one's pre-image. d++.me/pre-image. Too easy. Say it one more time. Be sure you're on the correct URL. It's d++.me/preimage. It'll redirect you, but make sure you're on the current difficulty, which is d++.me/preimage. That's right. All right. You got it on the correct difficulty target? Let's hear. 6265262 654. You got it. All right, 6226 2654. Who was that? All right, do you want 250K sats? You do? All right, you're getting 250K sats. Come find me after. Bitcoin, on-chain, Lightning, whatever. All right. All right. How does everybody feel about mining? Is it way less complicated than you previously thought? It's a simple brute force operation of guessing and checking random values that when plugged into the block header yields a hash less than a given target. And if you can find one, you get 6.25 Bitcoin, or if you're in my class, you get 250K sats. All right, there's no time for questions, unfortunately. If you got some questions, come find me after, okay? That's it.